I'm also ill, so if you hear me coughing in the back, sorry about that. But welcome to the third SLS of the year, the first of 2021. This time we've got Lazu. She's going to talk to you guys about cosmic ray propagation, a little bit about her PhD, all that sort of thing. So I will leave you.
All right. So I'm Vasu. I'm a postdoc right now at Propagation. And what I'm going to talk about today is ultra-high energy cosmic rays, so that is the UHECR, propagation in the galactic halo. So I will really encourage you guys. It's just like 4 of you. Just stop me in between if you don't understand anything. You don't have to feel hesitant. And if we don't finish the talk, it's fine. It's really okay. So you don't have to worry about that. All right. Sorry, I have to stay here. I can't walk around because I don't have a pointer to control this. Right. So the first thing I'm going to go through is like an introduction to cosmic rays. Have you guys ever heard? I suppose you've heard about cosmic rays. Do you know what they are? No. All right. That's my job to tell you. So, what are cosmic rays? Now I'm throwing like a very scary figure at you. Trust me, it's not that scary. It's the most basic. Basically, what this figure is showing you, or what I'm going to try to explain to you, is like, first of all, cosmic rays are neither cosmic nor are they rays. It's a very misleading term. It's old nomenclature. They are mostly non-thermal particles. When I say non-thermal, that just literally means that they don't follow the Maxwellian distribution that you guys might be familiar with. All right. So they are non-thermal particles. They can be protons, electrons, combination of different species of elements. So it could be iron, all of that. And basically, this line that you see, can you see my cursor? Can you see this mouse? If I'm moving, can you see the mouse?
Yeah.
Okay. So what you see here, this is basically the cosmic ray proton. So this is on the y-axis here. You see is the intensity of the cosmic rays that we see at Earth. On the x-axis is the energy. Now, do you guys know what is the GeV, EeV, EV? So this just means giga electron volts. So we are talking about quite high energy. So it's going up to 10 to the power 19 electron volts, or 10 to the power 19, which is basically an EeV, exa electron volts. This is a very common terminology we use in cosmic rays. So we stick everything that we do, we think in EV energy rate. This is an astroparticle convention. And what's interesting here is that this green ellipsoid that you see, this is showcasing protons. The blue one is for electrons. And generally the ratio of protons to electrons that you observe is generally like 100 to 1. So you generally, for every electron that you see, you're seeing about 100 protons. So that's what roughly cosmic rays are. And there is a very creative nomenclature as how we define cosmic rays. So you have high energy, which is this pink band, then you have very high energy, and then you have ultra high energy. And basically, to understand why do we have this kind of demarcation, the reason is that there is this region called the anchor, and you're demarcating where the cosmic rays are coming from. So generally, the ultra high energy cosmic rays are thought to be the cosmic rays that don't originate within our galaxy. And your next question might be, then how are they produced? I will get to that. That's basically what I want to talk about. But before that, I want to tell you quickly about how we observe cosmic rays. So generally, cosmic rays are observed, at least the very high energy ones or the ultra high energy ones are observed by the ground-based detectors. These are Cherenkov detectors. So they are basically, you have detectors in water tanks, and you are looking for the Cherenkov phenomena where you know that the particles can go more than the speed of light in a different medium, and that's how you're trying to detect them on the ground. There are also balloon experiments and some satellite experiments that tend to detect cosmic rays, but they are looking at generally slightly lower energy. So this basically tells you how you observe cosmic rays. Now the question is, how are the cosmic rays produced? So anything that you see below what we call this NEAM, again, creative term, anything below to the left of that are basically galactic cosmic rays. So they can come from sun, they can come from supernovae, they can come from stellar clusters, or the galactic center. We don't know exactly where they come from and why we don't know. I'll get to that. But that's what we call generally a galactic cosmic rays. And then the extragalactic cosmic rays are everything that's like versus green. So when I say extragalactic, that means they're coming from outside the galaxy, from other galaxies, aliens, we don't know. But that's what extragalactic cosmic rays are. So they can come from active galactic nuclei. These are just galaxies which have a supermassive black hole in their center, and they have large activity. They can come from starburst galaxies, which are just bigger galaxies which have higher star formation rate in the center. So they produce many more stars than as you compare it to Milky Way. So that's how it's a bit relative term. And then you have gamma ray bursts, which are objects which emit gamma rays in certain time durations, and they might also be having cosmic rays. So they generally, if you can think of it, it's like say a neutron star merger will be ejecting gamma rays. You'll have a jet, and from that jet you'll also have cosmic rays. But the point is that I kept on telling you that we don't know where they come from. And why is that? The reason is, now assume that, think of this star as a source of ultra-energy cosmic ray. This yellow region that you're sitting in is the extragalactic space. So basically any region between the Milky Way and your cosmic ray source. This blue circle is us, is our galaxy, and we are centered in here sitting as the observer. So now imagine that this cosmic ray starts from the extragalactic space and it's going somewhat straight and coming towards the Milky Way. However, what happens is, as you know, charged particles will deflect in magnetic fields. That's why I said that the extragalactic space has weaker magnetic fields, but within a galaxy, we actually have relatively strong magnetic fields. If you want to have a relative number in your head, within the galaxy, we think that the magnetic field is of the order of few microgauss, whereas extragalactic magnetic fields are at the order of nanogauss. So a particle will deflect way more in the galaxy than outside. So what happens is, the particle enters the galaxy, it deflects a lot, and eventually when you're observing it here at Earth, you will think that it's coming from this direction, because generally you see something coming from there and you'll be like, yeah, that's the direction. But in reality, what has happened is that the particle has just undergone multiple deflections. So that's why when you look at a cosmic ray, it becomes extremely hard to know where it comes from. And this applies to all kinds of cosmic rays. It could be galactic, extragalactic. The cosmic rays will always undergo deflection, so the localization as to where it came from is an extremely hard thing to do. Because to do that, you will need to know the structure of magnetic fields in the galaxy, so you can back calculate things and say like, okay, yeah, that's where it came from. So that's a hard job. So now within this field, people have proposed multiple models of galactic magnetic fields, how the magnetic fields can be in the galaxy. However, I'm just using two models here as an example. The end of these lines is basically pointing to where you're seeing. But based on these models, your cosmic ray could be pointing in this direction, coming from this direction. So we are back calculating here through these fields, or it could be coming from this direction. So these models are not consistent. We don't have any consistent understanding of how the particles are coming, or where they're coming from. So that's one of the reasons why we don't understand this is because there are structures within our Milky Way, in the halo of the Milky Way. I'll get to that, what I mean by that, which we don't model because we do not understand, because we have the incomplete knowledge of the halo of the Milky Way. We are unable to model the magnetic fields very well, well, if we can't model the magnetic fields very well, we struggle with understanding where the cosmic ray comes from. Also, we struggle with understanding where the synchrotron data comes from, or the radio sky. If you guys must have seen the CMB sky. You've seen the CMB sky, so that's what I mean by radio sky. I'll get to why I'm talking about that in a minute. But there are multiple open-ended questions when you are talking about magnetic fields in the galaxy. So, the next point, if you remember, I said structures in the halo of the galaxy. Have you guys heard of the Fermi bubbles? Anyone? No. Okay. So, about 12 years ago, the Fermi Lab, it's a satellite telescope instrument, detected the Fermi bubbles in the gamma ray regime, so in the gamma rays. And these bubbles are basically, so this is the plane of the galaxy. This means this is the disk. This is where we sit. And these bubbles are actually extending vertically or perpendicular. So vertical is the wrong word. That's perpendicular to the plane of the galaxy. So they're going outside the galaxy, and they're called Fermi bubbles, which is shown here in red. We did not know that they existed. There was some indication in some data sets, but it was only with the Fermi bubbles that we were really sure that there's definitely structure out there. Because generally when you think about the galaxy, you always think about the disk. You never think about anything above and below, like the top and bottom. You never think about that. And then a few years ago, a Rosita, was an X-ray experiment, again space-based instrument, which saw even further extended bubbles. They were called the E-Rosita bubbles, and they were seen in X-ray. So Fermi bubbles were about, are you guys familiar with the length scales of kiloparsecs or parsecs? Does it give you a feeling? No? Oh yes, kind of. So if I'll give you a reference number to remember. 1 kiloparsec is about 10 to the power 21 centimeters. Okay? That is very hard to remember, but like in AU, it's about, okay, I'm forgetting now. Do you have a feeling of AU, like astronomical units? Let me give, because let me give you, so right, 1 kiloparsec is about 10 to the power 8 AU. Is already quite a lot. I know that this is very big numbers that I'm going to talk about numbers at a very massive scale, and it will be hard for you to wrap your head around it. But if you want to think about that, I'm saying that these bubbles are like 10, 15 times distance from the sun. That's how big they are, and that's like in one direction, and in the other direction as well. So the disk, the galactic disk, is said that it's about 30 kiloparsecs. 30 kiloparsecs is like 3,000, like 10, 30 kiloparsecs is about going to be 10 to the power 10 astronomical units, roughly. But I can't give you it's very hard to give you the feeling of numbers at this scale because they just feel absurd. But the point is, they're large. They're as big as a disk, but in perpendicular direction. Okay? So it's just like something like this. So we realized that there is stuff out there. If there are particles out there, that means there will be magnetic fields out there, which means that all this while, when people were modeling the galactic magnetic fields, they were just thinking about the disk. So they would think that our disk has a spiral arm, so they would model mostly the fields in the spiral arm, and just ignore these very large scale regions because people would think you don't see anything there, so there wouldn't be anything there. But that's not the case. Right, and also in radio, so I talked about gamma rays, X-rays, also in radio you see about some extended structures, they're called the haze. This picture is a bit misleading on my part because generally you've only seen these hazes in unpolarized emission. So radio emissions are generally polarized or unpolarized. So generally you're seeing this haze in unpolarized, but we suspect that they also exist in polarized. It's just hard to detect these things. And some back of the envelope calculations and assuming really very basic toy models, you think that the fields in these regions, in these bubbles, could be as high as 4 to 12 microgauss, which means that if the disk, which is generally has a roughly field of 2 microgauss, you're talking about fields in these regions 3 to 5 times much more. So that means that the particles that are coming from outside, the cosmic rays that come from outside, they sit for much longer time in the halo than the disk, which makes sense, right? The halo is huge, so they are going around in the halo much longer than the disk, and so it is important to account for the halo when you're modeling galactic magnetic field. So this brings me to the first part of my PhD, which is my work was to model magnetic fields in this halo region of the galaxy. And to do that, I had like a very simple, looks complicated, but basically it's an exponential profile. It's just an exponential cutoff. So the field cuts off over a certain distance exponentially, that's all. And what you see here is just the cross section in x, y, and x, z direction. So the arrows tell you how the fields are. So it's a toroidal field. Do you guys know what's a toroidal field? Right, so the fields are going in one direction above the plane and the other direction below the plane. So when you're looking at the curl, like the current will remain conserved. So that's what a toroidal field is. And we have evidence that the field in the galaxy might be of toroidal nature. I did not invent this. We have some evidence which suggests that the field might have this nature, so we went with the simplest model. And, excuse me, we introduced turbulence. Have you guys done turbulence in your courses? Okay, so what we did is, it's a very simple turbulent field model. So it is far from reality. It's generally a toy model, and basically we are using an isotropic turbulence, which is also called the Kolmogorov turbulence. It has the power, it's called a 5/3 turbulence because the energy that is injected here goes to the lower length scales and follows a 5/3 power law. So this is the injection scale. So you inject energy at larger wavelengths, or however you understand, eddies, and then that cascades to lower wavelengths and follows a 5/3 power law. So we had like a simple turbulent field model, and we needed an electron distribution for the galaxy. I'll explain why we needed this electron distribution. So we had like a magnetic field, we had a simple electron distribution for the galaxy. Now this electron distribution is also exponential, and you will see that I'm using same numbers, this 5 and 6 kiloparsecs. So that's the radial cutoff, and that's the azimuthal cutoff. And this hyperbolic sec squared actually behaves a lot like an exponential. Now, with the magnetic field and the electron distribution together, you get something which is called the synchrotron radiation. It's similar to cyclotron radiation. Cyclotron radiation is when a particle is gyrating in the magnetic field, and when it gyrates around the magnetic field, it emits a radiation. And in synchrotron, the particle is gyrating at the speed of light. So that's the only difference. The speed of light, that's the major difference, sorry. So that's why I was using the word non-thermal, because when you're saying something is non-thermal, your non-thermal electrons, when they sit in the magnetic field, they're going to emit synchrotron radiation, and this synchrotron radiation is what is observed in all the radio surveys that you're seeing at low frequency. So Planck, WMAP, all of them, when they observed generally in polarized intensity was synchrotron radiation, total in polarized intensity, and in total intensity or the unpolarized intensity, they also saw some other radiative mechanisms, but it was predominantly synchrotron and polarized. I'm not going to go through this integration right now because we are running short on time, but I want to explain to you synchrotron in a diagram way. So, how do you get polarized synchrotron radiation? Basically, you can imagine, maybe I'll have to go back to this. Basically, you can imagine that synchrotron radiation is given by this expression, all right? This expression, what it's actually saying, I'll go step by step. So, this is the distribution shape of the synchrotron radiation. This is basically called the synchrotron kernel, which you're convolving with the electron density. And why am I using these weird differential numbers and not just like a variable? That's because, first I had to do this because my supervisor had asked me when I started my PhD. But there is a logic to it. The logic is that when you observe something, astronomy or anything, you always observe it relative to something. So you are observing something in an energy bin or within over a certain time or over a certain area. So you're generally seeing differential quantities. So when I say dn d log E, I literally mean the number of particles within that energy bin. That's basically what it means. And you integrate it over all the energies of the electrons possible. And this is just a scaling factor, so you can ignore that for now. So basically, when you think about polarized synchrotron radiation, I would like you to think of it as, how to explain in the blackboard. So the polarized synchrotron radiation tends to have, I'm really struggling here without a board. I was expecting there to be a board. Okay, and understand like this. When I said synchrotron radiation occurs when electrons gyrate in magnetic field. Now, when you're observing, as an observer, you have a line of sight, right? And you have, line of sight is the sight along which you are making an observation. Now, synchrotron radiation actually occurs in magnetic field, which is perpendicular to the line of sight of the observer. So your magnetic field is sitting, let's say there's magnetic field in this room, right? There is. The magnetic field can be sort of resolved into something called perpendicular and parallel components. So if I'm seeing in this direction, I have a magnetic field which is parallel to my line of sight, but there's one also which is perpendicular to the line of sight. So when you see synchrotron, generally what you're seeing is going to be the magnetic field which is perpendicular to the line of sight. And what you do is you can think about synchrotron polarization and you can resolve it into two directions, which is called the perpendicular and the parallel polarization. And what you do is you imagine synchrotron, I don't know if I'm making it too complicated for you or if it's going, if you don't understand, stop me because maybe I'm making it too complicated for you. But the idea was that you can imagine along the line of sight, you divide your line of sight into steps, which are your what you call integral steps or dn steps. Now, at each step, you can imagine the emission from synchrotron to be something like an ellipse. Why am I? It's not the reason why I'm saying it's like ellipsoid is because generally your parallel and perpendicular polarization will have a major and a minor axis, which forms these ellipses. And at each line of sight, because your magnetic field changes direction, your ellipse will change direction. And the sum of all these ellipses is what you see. So if the ellipse angles are aligned perfectly, you will still see a resultant polarized synchrotron emission. But if they don't align, or if they align in a way that they cancel out each other, you don't see any polarized emission. So basically that was, like maybe this part, I'm not doing a good part, it's a good job explaining. Anyways, getting to the fun part. So we wanted to compare, what we did is, I did some modeling of synchrotron radiation, and I produced some emission maps. Now what you see here is a sky map from Planck. And what we did here is that we did some smoothing to the data. So this is the same Planck sky map, CMB sky map that you are used to seeing, but this is at 30 gigahertz. And what we have done is we have smoothed out the map a bit. We have removed the galactic disk because we were not interested in modeling the galactic disk. And we've removed certain regions. And then what we did is we said, okay, let me produce the same synchrotron radiation from my model and compare the two. Now, this is a very preliminary comparison between model and data, but we about, we found that generally you can have a magnetic field in this halo about around 4 to 7 microdals. And the cutoffs that I was talking about, the exponential cutoffs, they have to be around 5 to 6 kiloparsecs. Now this is a very rudimentary first-hand comparison. The model lacks a lot of complexities. We made certain assumptions, which are now in hindsight, now that I work on this more, I realize maybe I shouldn't have done. But this is how science works. You work on a project, you write a paper, you finish writing the paper, then you become very dissatisfied with it 2 years later because you realize you made some mistakes. But that's just progress. So there are issues with this paper, or this work, but that's just in hindsight and later. All right? But even then, when we did the same comparison, so what you see here are 2 different models which are also quite popular. Those models were also unable to fit to the data. In fact, our model was fitting slightly better to the data. So that was a promising start. Why? Because in these 2 models, the halo that I've been talking about, they are very weakly modeled, in the sense that the field strength there is quite weak. Which means that at least if you want to match to the data, you need strong fields. So that was at least one step. It was that, okay, our model is not very good, but it's better than some of the others. So, yay. But you would think like, oh, you started with all these cosmic rays, but then you deflected to synchrotron. Why? Well, that's what the reason why. I needed to model first the fields, and I needed to validate that models against something. I couldn't just say, oh, this is the model, and just like start running simulations. I needed to prove myself that what I'm thinking is actually in the right direction. Okay, so now we get to the second part, where I'm going to talk about cosmic rays. So in the beginning, when I started the talk, I was telling you that if you know the magnetic field of the galaxy, you can take your particle and you can backtrack it, right? What do I mean by backtracking is that if you start with, imagine this to be Earth, okay? And this yellow circle to be a galaxy. Basically, if you start from here, if you know the fields, you can backtrack it to different parts of the sky, and you will know where the particles came from. So this is what we did. We did backtracking of particles with our magnetic field model and other magnetic field models to compare how they look. So when we did that backtracking, we find something interesting. On the bottom here is a sky map that is observed by the ground-based observatories, one of them being Auger, the Auger Observatory. And what they see is that, now this sky map is in galactic projection, which means this is your galactic center, and this is your plane, and we see that there are 2 hotspots. So what you're seeing here is actually this Lie mass significance basically is just telling you the flux. So there is these red regions are just 2 hotspots that we are observing, and in one of these hotspots actually sits an active galactic nuclei in that direction, and that's called Centaurus A. And in the bottom here is a starburst galaxy, which is called NGC 253. Now, by no means am I saying that these 2 are producing cosmic rays. By a matter of luck or chance or whatever, in those 2 directions, we know that there are 2 energetic objects sitting. So what we did is we decided that we are going to backtrack our cosmic rays and look for hotspots around these regions. And we found that actually in our model, we can create, not quantitatively, but qualitatively, we get similar hotspots around the Centaurus A region, which is here in the purple star, and NGC 253 region, which is the starburst galaxy. So it's not exactly the same, of course. Why? Because again, the model is very simple. There's a lot of details that we're missing, but we're at least able to create those hotspots. And then we did the same thing with other magnetic field models. So this is another magnetic field model, and you can see that the position of these, like the distribution of these directions. So these are the directions, presumed particles, imagine, that are coming in. that gets shifted in some of the magnetic field models. So at least in our modeling, what was consistent is the position and the centering of this hotspot. So that was a good, positive step. So this is what was interesting for us, because in our modeling we had already proposed that we have very strong magnetic fields in the halo. So we came to the conclusion that if you want to reproduce something that looks like this, you will need a lot of magnetic fields in the halo to sort of spread your cosmic rays. So yeah, what it does, it focuses on high latitude structures. That's what I meant by high latitude. It fits better to the radio data, and there is a reasonably good qualitative comparison between the cosmic ray arrival directions from the observation and our model. The final thing that I did was actually trying to study another phenomena, which is basically, imagine, so in this case, as I said before, I told you that my model has two parts. There's a toroidal field and there is a turbulent field. So I wanted to do a theoretical study. So what I said is like, okay, I want to study how cosmic rays diffuse. Now diffusion intrinsically is related to turbulence. Okay? So I said I will turn off all the structures in my magnetic field model and just have pure turbulence and just see how the cosmic rays are behaving. The reason being that on very large scales, magnetic fields lose structure. Like when we say structured fields or turbulent fields, basically what we are talking about are length scales. At a certain length scale, everything remains structured. If you go outside that length scale, maybe it starts showing different patterns. So we wanted to just have isotropic fields, and we wanted to basically create this sky map that is again seen by Auger. It's called I'm saying large scale arrival directions at low energies. That's just because here we are looking, is it raining? Oh, wow. Here we are looking at the cosmic ray distribution at smaller energies, and what we are seeing is something like a dipole. Now, have you ever seen dipole in astronomy before? Have you seen in CMB? It's a very big.
Yeah. Somebody exchanged them.
Yeah, so this is, but this is not, this is, well, here the word dipole is being used quite in the dipole sense, so literally a cold spot and a hot spot.
Right.
Rather than having multiple cold and hot spots, you have a cold spot and a hot spot, and generally when you have like this kind of distribution, you're like, there has to be some bias from somewhere. So like somewhere you're getting things more than the other place in that sense. So basically the cosmic ray hotspot or dipole literally is saying that when you have where the dipole, where the hotspot is intensified, so this direction, we just literally say from that direction we seem to getting more cosmic rays, from the other direction not. And why does this dipole exist? We don't understand entirely, but basically the idea is that Milky Way sits in something called the Council of Giants, which is basically a distribution of other galaxies and objects. So it's like now we're talking about very large scale, so for reference, we're talking about megaparsecs here. So forget kiloparsecs, we're talking about megaparsecs, so this is large scale distances. And if you think intuitively, of course all these objects are not in one line, right? Some are closer to us, some are further away from us. Now, again, it is intuitive to think that the objects that are closer to us might give us more cosmic rays because we are close to them, so you don't lose them on the way. Whereas the ones that are further away from us, we might lose those cosmic rays in the way. And we're not talking about distances which are like, we're like talking about astronomical distances. So the idea behind the dipole is that you have probably some objects which are very close to you, so you get more cosmic rays from them, and hence this dipole, and some that are very further away from you. Now, I don't know if there's too much information for you, so you can ask me to stop, but there's a caveat. This dipole is very weak. So you see this nice coloring, but that's after smoothing this entire map by large angular scales, about 45 degrees. We are smoothing it. So this dipole is really weak. Generally, the cosmic ray distribution in the sky is isotropic. Why is it isotropic? Because it's literally Gaussian noise, like it's just random, right? Like if you have things coming from all directions, they will isotropize and everything will just become flat. So generally, on cosmic ray distribution, it doesn't, you cannot like look at a map and say, oh, like I see a dipole. No, you have to like smoothen it out to like get rid of these fine details, and then you're like, huh, I can see some pattern. So next time when you're listening to any talk or anything like that, always try to ask them the question, are you seeing the things the way you're showing me, or are you doing some treatment to the data to pull out that information, okay? So I'm gonna go to the electrostatics very quickly. I hope that you've seen the equation on the right. That's your Poisson equation. The one on the left is the cosmic ray diffusion equation. Now all of this is color-coded. What I'm trying to show you here is that in physics, by extension in any academic field, you can rely on analogies because equations seem to look very similar and have even similar functional forms. So that's your dielectric permittivity. As you said, you guys do electrostatics or electromagnetism, right? So you've seen this equation. This is your cosmic ray diffusion coefficient, okay? This is your potential. Here, this is the cosmic ray number density. Now you can say, oh, but this is potential, this is density. They're two different physical quantities. And you're right. But I'm just trying for you to look at analogies. The same differential delta square operator is acting on it. We are trying not to say one is the same as the other. We are just trying to see a proportionality, that something behaves similarly, because if something goes as 1 over x squared, the x could be anything, and that's what I'm trying to get at, right? That is your volume charge density. In your Poisson equation, here this is the cosmic ray source, or like the injection where the cosmic ray is coming from. So basically, if you do a bit of math, what you find is that the cosmic ray dipole is actually proportional to the diffusion coefficient and this grad n over n, which is similar to the electrostatic dipole, which is proportional to the dielectric coefficient, electric permittivity coefficient, and delta V over A. So it's the same proportionality. So how much time do you have? Oh, we don't have that much time. Okay, quickly. So this is just your electrostatic standard analogy. What we've done here is said that there's a dielectric coefficient inside, which is actually weaker than the one outside, and what you see here is a shielding effect. You can actually, this is basically your undergrad physics. You can simulate this. This was just done on simple Python. There's nothing immensely important happening here. What I'm trying to get to you here, because we have less time, basically to say, within our galaxy, we can imagine us sitting in different diffusion coefficients. So there can be a diffusion coefficient for instance, as an analogy, the Milky Way, the solar system sits in something called the local bubble. Have you heard about the local bubble? Okay, no. Local bubble is just a little region within our Milky Way in which our solar system sits, and it's about 300 parsec, not kiloparsec, parsec. So it's a very small region. But the point is that this diffusion coefficient within the bubble, if it is smaller than the one which is outside, you will shield some of the cosmic rays. Because what will happen is your particle will not be able to enter. And that's the shielding effect that I was trying to show you here. So this is getting shielded. So what happens is, here what you see in this on the x-axis is basically your different diffusion coefficient. And on the y-axis, I'm showing you, we have time to do, right?
Yes, I think we're going about 5 too, so.
Okay, I'm done. This is the last slide.
Yeah.
On the y-axis, what I'm showing you is the dipole strength that we And basically what I wanted to tell you is that if you go through different diffusion coefficient, if you go from a higher to the lower one, you start suppressing the dipole. Now this is more complicated right now to get into actually, because we don't have that much time. But okay, one thing if you want to take away, because I can't explain all of this, we don't have time anymore. One thing if you want to take away and can take away, then it could be that you can actually use analogies to study astrophysical phenomena in different systems. So here I used electrostatics as an analogy to study how cosmic ray diffusion works. It's a difficult problem. We didn't know how to start, so we started thinking what is analogous to it. And that's what we came up with. But anyways, yeah. I'm not going to go into more into detail because I tried to squeeze like a 45-minute talk in 30 minutes, so it was a bit hard. But feel free to reach out to me. You can ask me questions now or just write to me if you're interested. Yeah, go ahead.
Quick question, just going back to the scale.
Yeah.
So this model as superphons, specifically at very high energies.
Yeah.
So I'm assuming if the antiprotons then don't quite be annihilated and
Yeah.
we'd observe them as lower energy gamma. However, is there a reason why regular protons are observed instead of say
Regular protons are observed
instead of particles?
No, you do. Well, sorry.
At highest energy scales.
No, so the thing is, you do observe neutrinos, right? But the neutrinos, they decay in energy, so you can only observe up to certain neutrinos. You do observe other muons and other particles, but in this figure, I just wanted to show you that I was interested in cosmic rays because I was interested in looking into synchrotron, for which you need cosmic ray electrons or protons. You do have synchrotron radiation from protons also, but that's much weaker. But no, you do see different particles. It just depends what energy you're sensitive at, because other particles might decay to lower energies, and then you need different detectors, and you need to look at different energies.
So it's just more like detectors to detect other energy levels?
You mean for cosmic rays, or you mean for other particles?
Just I guess that diagram itself.
No, so we do, again, the particles, I'm just trying to think if I'm answering your question correctly. You have other detectors to see different particles. So like you have neutrino detectors, for example. But they are going to be working at a much lower energy scale. They go up to TeV. So you don't see neutrinos at 10 to the power 19 TeV. Like, you won't be able to explain them. We've never seen, we've not even seen neutrinos at, I think it's only now recently we saw something at TeV. So yeah, it's different detectors look at different things. This is only for cosmic rays, so that's why you're only seeing this range. Anything lower than 1 GeV, we don't call it a cosmic ray anymore. So the terminology changes. But yeah, and also it will be harder to observe them because they probably interact and you lose them.
So I'm guessing it's that, on that diagram, I'm guessing the proton stats are able to be observed at the highest.
Yes, yes.
Is that just simply because they don't interact as much as other particles do?
The electrons, it all boils down to their cooling scales and length scales, and the protons are the ones that survive at those energies.
Yeah.
So others, yeah, in broad terms, yeah, others don't survive, so you don't see them.
Okay.
I think we take this 15 minutes more if anybody has one more question.
Yeah, of course.
If you have any other question, otherwise feel free to reach out to me if you're just interested in this topic. I didn't do that good job in explaining all of it, so I'm also doing this for the first time. So feel free to ask me.